Assalamu alaikum you all. Welcome to the lecture of chemistry. I am your teacher Sumayya Khan and we are studying the chapter transition and inner transition elements. We have almost completed this chapter. Only a small portion is remaining, and what is that portion which we are going to learn today is actinoids. What are actinoids? Actinoids are the group of 14 elements from thorium 90 to lawrencium 103, which are placed at the bottom of the periodic table. These actinoids constitute the second inner transition series. The first inner transition series was lanthanoid, and this is your second inner transition series known as actinoid or 5F series. Okay. Now actinoids belongs to the third group of the periodic table in the seventh period. All of us know that the periodic table is made up of 18 groups and 7 periods. Okay. Now out of these 18 groups, your actinoid interrupts the third group of the periodic table, and the seventh period of the periodic table, the seventh period is also your fourth transition series. So it actually interrupts the third group and the fourth transition series. As there are 14 elements, that is why they are not placed at that position of the periodic table, and for convenience and for symmetry these 14 elements are placed at the bottom of the periodic table like lanthanoids. Okay, as we know that these are inner to the transition element actinium, that is why they are known as actinoids. Due to its resemblance with the element actinium, all these 14 elements are together termed as actinoids. Okay. The general electronic configuration of actinoid is represented by radon 5F 1 to 14, 6D021, 7S2. For convenience of writing the configuration, we can take the help of the electronic configuration of the noble gases. So radon 86 is the noble gas which we use for convenience for writing of the electronic configuration. After 86 electron, the next two electrons will go into the 7s orbital. 7s is your outermost principal shell here. So the next two electron will go into 7s orbital in all the actinoid elements. So this is how 88 electrons are filled. After 88 electrons, we have the 89th electron and so on. Now these 89th and so on electrons may go into penultimate 6d orbital and then to pre-penultimate 5f orbital. So the actinoids involve the filling of 5f subshell or orbital. Now these are the 14 elements which are together termed as actinoids. Thorium is 90, then from 90, 91, 92, 93 like that. In the end we have lawrencium 103. Out of these 14 elements, only thorium and uranium occurs in nature. It means they are naturally occurring, and all the remaining elements are what man-made or synthesized during the reaction. They are observed to be produced during the nuclear reactions. So all these 14 elements are also radioactive in nature. It means they may undergo radioactive decomposition or radioactive decay. But the half lives of these elements, of the especially the upper actinoid elements, is very high. The half life of uranium is I think 2.14 into 10 raised to 10 years. So it will take lakhs of years to undergo decay. Okay, so the half lives of some of these actinoid elements are very high, and the half life of some of the actinoid is very low. Okay, Now all the remaining after thorium and uranium, all the other actinoid elements are produced as the radioactive decay product of these uranium and thorium. All these elements exist in many isotopic forms, okay, and out of which only one or two isotopic forms are useful. Here electronic configuration of actinoid is also given. You can observe that in all the actinoid element, the 7s orbital contains the 2 electron. In some of the elements, 6d orbital will have 1 electron, or in some it will not have. Actually, it is observed that there is some uncertainty observed in their electronic configuration. One element may exhibit more than one kind of electronic configuration, where it may be observed that there is one electron present in the 6d orbital and there may be no electron in the 6d orbital. Okay, so there is uncertainty in the electronic configuration of the 5f series. Okay, but most of the time you will observe what the 5f orbital is progressively filled. This is the valence shell electronic configuration of actinoid, which is same as that of lanthanoid. Okay, where your outermost shell contains the 2 electron, then penultimate d orbital may or may not have 1 electron, then your pre-penultimate f orbital may contain, will get the valence electrons. Okay, now let's talk about the oxidation state of actinoids. Actinoids exhibits variable oxidation state from +2 to +7. From this diagram you can see that out of all these oxidation state, +3 is the most common oxidation state shown by most of the actinoid elements. Now why this is happening? Because why we are observing the wide range of this variable oxidation state, we can say that the reason for is that the 5f, 6g and 6 orbitals, 6s orbital have similar energy. It is not 6s, actually it is 7s. Sorry, it is written wrong here. The 5f, 6d and 7s orbital are of comparable energies. It means their energies are quite similar. So the electron from all these orbitals may go and take part into any reaction or bond formation, resulting in the variable oxidation state. Among these, +3 is the common oxidation state shown by most of the actinoid elements. There are few properties of actinoids mentioned here. Many properties are there, but few are mentioned. Some are not mentioned, like they show very high melting and boiling point. Their density is very high. These are also important properties which are not mentioned in here. Okay. Now let's see what is mentioned here. They are silvery white in appearance and display a variety of structures. Like lanthanoids were silvery white, actinoids are also silvery white. Okay, like lanthanoids, actinoids also show actinoid contraction. We have learned about the lanthanoid contraction and the cause of lanthanoid contraction in our previous lecture. The same reason is for actinoid contraction. Poor shielding of 5f orbital and increased effective nuclear charge results in the actinoid contraction. Now actinoid ions are generally paramagnetic because they contain unpaired electron. We have learned about the this paramagnetic character also. Actinoids are generally colored. Actinoids have greater tendency to form complexes in comparison to lanthanoid because their charge to size ratio is good. It means that they have higher charge and smaller size. When we'll discuss about the actinoid contraction, you will find that the actinoid contraction is greater than the lanthanoid contraction because the shielding effect of 5f is more poor than the 4f orbital. because of which what happens, the contraction in the actinoid series is greater as compared to the lanthanoid series. And because of this, what happens, the charge to size ratio becomes good. It means they have higher charge and smaller size, and they become more reactive. That is why actinoids have greater tendency to form complexes than the lanthanoids. Now, application of actinoids. There are many application of actinoids, and one should be known by most of you that these actinoid elements like uranium is used for making what, the nuclear power plants as well as for making nuclear bombs. Okay, now one is mentioned here is what, that as we know that the half lives of the natural thorium and uranium isotopes are so long that very negligible radiation from these elements are observed. We know that uranium is radioactive, thorium is radioactive, but they are not very harmful. You will not get affected by touching uranium or thorium, okay, because their radioactivity is happening at a very slower rate. Okay, they are decomposing at a very slower rate. Now thorium oxide is used with 90, when you take 99% thorium oxide with 1% cerium oxide, you will get an incandescent lamp, which is a very good uh, source of heat and light. Okay, even today there is a great demand for these lights for outdoor camping. It was used earlier before incandescent lamp came into existence, but nowadays we generally don't use these lamps. Okay, the people who are going for camping, for hiking anywhere, they take these kinds of lamps. Okay, 1% of cerium oxide is very important, because if we will not mix it, the light which we will get from these lamp will be very poor light. So it enhance the light, the 1% cerium oxide enhance the light which we get from this thorium oxide lamp. This is one example, a thorium based gas mantle, okay, which are available in the markets. Now, what are the similarities and differences between actinoids and lanthanoids? Let's see the similarities first. Both the series show a +3 oxidation state. We know that lanthanoid as well as in actinoids, both these lanthanoids and actinoids interrupt your third group. That is why their +3 oxidation state is the most common oxidation state shown by both lanthanoid as well as actinoids. But the variation in oxidation state is more in actinoid than in lanthanoid. So differences में क्या आ जाएगा, lanthanoids show a maximum oxidation state of +4, whereas actinoid will show the oxidation state variation from +2 to +7. Okay, now come to the second point. In both the series, the f orbitals are filled gradually. We know that in lanthanoid as well as in actinoids, the f orbitals are filled, the pre-penultimate f orbitals are filled progressively. But in case of lanthanoid, we fill the 4f orbitals, and in case of actinoids, the 5f orbitals get filled. Now let's come to difference. Lanthanoids do not form complexes easily, whereas actinoids have a greater tendency to form complexes with ligands such as thioethers. The reason is same. The actinoids are more reactive due to their greater charge to size ratio, and they have the greater tendency to form complexes. The third point is ionic radius of the element in both the series decreases with increase in atomic number. That is, we observe lanthanoid contraction as well as actinoid contraction. But actinoid contraction is greater in comparison to lanthanoid contraction. The difference is all lanthanoids are non-radioactive except promethium, but all actinoids are radioactive in nature, that we have discussed. All the lanthanoids are what? Non-radioactive except promethium, which is also man-made. It is not naturally occurring. Promethium does not occur naturally. Whereas in actinoids case, what happens? All the actinoids, all the 14 actinoids are radioactive, and out of 14, we can say only two, actually more than two exist, but here in your syllabus it is mentioned that only thorium and uranium occurs naturally. The next one is the electronegativity of all the elements in both the series is low and are said to be highly reactive. We know that they are termed as lanthanoids and actinoids are termed as inner transition metals, and metals have very low electronegativity. So like that, these lanthanoid and actinoid also have very low electronegativity and are highly reactive. Now let's come to difference. Lanthanoid do not form exocations, but actinides forms oxocations such as uranium oxide, plutonium, neptunium oxide, etc. Okay. The nitrates, perchlorates and sulfates of all these elements are soluble, while the hydroxides, fluorides, carbonates are insoluble. It means that both lanthanoid and actinoid can form the compounds of nitrates, perchlorates, sulfate, hydroxide, fluorides, and carbonates. Out of these, for lanthanoids as well as for actinoids, some are soluble and some are insoluble. Now the last one, most of the lanthanoids are colorless in nature, whereas actinoids are colored ions. Actinoids show color, whereas lanthanoids are most of the time colorless. Now what is post-actinoid elements? The elements which comes after actinide would be obviously would be called as post-actinide elements. Now before the formation of this F-block series, the element which we knew after uranium 92, the atomic number of uranium is 92. So the elements which were discovered after uranium were used to be called as trans-uranium element. So after uranium, whatever elements that are present in actinoid series can be termed as trans-uranium element. In the same way, the elements after the actinoid series, that is after 103 lawrencium, whatever elements are discovered are termed as post actinoid elements. That is from 104 onwards to whatever we have discovered till yet 118, these are called as post actinoid elements. Okay, now why they are called as post actinoids? Because they are similar to actinoid element. They can be synthesized in nuclear reaction. So far 9 post actinides elements have been synthesized, and their study is difficult because their half life is very less. So their existence is for fraction of second. That is why to study them in detail is very difficult. So here student, we have completed our chapter transition and inner transition elements. Okay, hope you will find these videos useful. Okay, now take care of yourself, study hard. Allah Hafiz.